So just to review our idea of similarity and how we've worked with that before, we're going to do this little chart here, and then we're going to see how that translates into our three-dimensional aspect to solids that we've been talking about. So similar solids have the same shape, but what's different about them? What would be different if they're the same shape, so 2 cones, 3 cones, whatever, 2 pyramids, what would be different about them? Different sizes. I mean, that does go along with dimensions, but just as a general concept. They're different sizes. What must be true about their measurements? They can't just randomly be different sizes. What has to be their relationship that holds them together and defines that similarity? Proportional. When we first introduced the idea of similarity, we talked about both angles and sides. For similar two-dimensional shapes like triangles, the angles have to be congruent and the sides have to be proportional. We don't really care about angles when it comes to 3D shapes, so we're just zooming in on that proportionality of their dimensions and measurements. What do we call the ratio of similarity that's all the way simplified? That ratio that represents the relationship, their similarity, scale factor. A couple of concepts that carry through that you want to make sure you remember. So here's an example of 2 similar cones. What would their scale factor be? Read from left to right. 1 to 2 with this notation, or you can write it as a fraction, 1/2. Okay. Whenever they don't specify what direction they want you to go in, you always go from left to right. Remember, scale factor does need to be fully simplified. Do you see any sides that actually have 1 meter or 2 meters? No. So remember, this is just a relationship. It's representing the relationship between the two. It's not saying that there is a side necessarily that's 1 or 2. Okay. It's just taking the relationships that are present in the picture and simplifying them. All right. So is that everybody familiar with that? Now we're going to talk about how can we take that idea and kind of translate it into what we've been talking about with areas and volumes. So in the first dimension, which is where our scale factor lives, it's in the first dimension kind of realm of geometry, our scale factor or our relationship is A to B. You replace those 2 with numbers, obviously. A to B. What do you think the ratio would be if I then turn it into relating the areas, which is in the second dimension? If it was A to B in the first dimension for scale factor, what would the ratio be in the second dimension? Okay, A squared to B squared. Guys, remember what happens to the units when we write the units for an area? What's the power that we use? 2, right? Squared. Centimeters squared is for area and surface area. So that's what happens when you move into the second dimension, everything's squared. What do you think it would be for the volumes, the third dimension? A cubed to B cubed. So this is our relationship that we have with the scale factor, then the ratio of the areas and the ratio of the volumes. Now, in addition to that concept, I'm actually going to draw a little diagram for you that's going to be incredibly useful. It's a staircase. This is how I'm going to kind of reference how we travel between the different dimensions when we're going back and forth, relating areas and volumes and scale factor. So if you draw this little staircase here, I'm going to label the first step as the first dimension, which contains the scale factor, or singular dimensions. So if I reference the scale factor, or I just pick one dimension, like height by itself, or the radius by itself, or the slant height by itself. If I ever mention just one dimension, I'm referring to this step here. The second dimension contains your area, whether it's surface area, lateral area, regular area for a flat shape, doesn't matter. And then third dimension is going to be your volume. Okay, so label all 3 steps, the first, then the second, then the third. Now what we're going to do is draw some arrows that represent our traveling up and down the steps and how we would do that. So if I was on the first dimension and I want to travel to the second dimension, what would I have to do to the scale factor to get there? Square. So the way that you get from the first dimension to the second dimension is by squaring things. What do you have to do to get from the first to the third? Cube. So if you ever run into questions, and I'll show you some underneath, questions where you need to translate something from the first dimension to the second dimension, you would have to square. Or if you're translating stuff from the first dimension to the third dimension, you would need to cube that. Okay, so this is showing you how you do that. What if I go down? What if I'm in the third dimension and I have stuff about volumes, but I want to kind of boil that down to talk about the scale factors. I have to cube root. And then if I want to go from talking about the relationship from areas and go down to talk about scale factor or single dimensions, what would I have to do there? Square root. So this little chart here is going to be really helpful in understanding how to go up or down the staircase between dimensions and how you would do that. Now what do you notice is missing? What pathway do you notice is missing? 2 to 3 or 3 to 2. It's impossible to go directly from the second dimension to the third dimension or vice versa. So you're going to have to take an indirect route. What if I had information about volumes and I wanted to find a relationship with the areas? What would I have to do? You would have to go down to the first dimension and then back up to the second. So it's a longer pathway. There's no direct way to get from the second to the third dimension or back and forth. You have to go kind of roundabout. Okay, so just keep that in mind when you see questions like that. Okay? So the first kind of introduction to how we can work with this idea, the staircase, is this one right here. So it's a two-part question. I want to know, are they similar? Are these solids similar? And if so, what would the scale factor, the ratio of areas, and ratio of volume be? So how would you determine if they are similar? What have we done in the past? What would you do? Compare what? Compare the parts. Does it matter which parts that I compare? It does matter. You want to match or check the corresponding parts. So if I check, these are both 10, those are both 15. If I check that relationship to the relationship of the slant heights, it looks like that's what they're giving us. Would those be the same? Are those corresponding ratios the same for all the dimensions? No, they're not the same. So would these be similar pyramids? No. If your answer is no, you would then move on. There's no scale factor or anything beyond that if the answer is no. What about these cubes? 3 to 6, 3 to 6, 2 to 4. Are all of those relationships the same? Okay, so these are similar. Now we're going to write the scale factor, the ratio of areas, and the ratio of volumes. So what would the scale factor be? First dimension would just be comparing the two, or a single dimension. So let's say you picked height or something. It would simplify to 1/2. That's your scale factor in the first dimension. How do I then compare the areas? How do I go up to the second dimension? You're going to square, just like we see here and in that staircase diagram. So what would your ratio of the areas be? 1 to 4. Then what would the ratio of their volumes be? 1 to 8. 2 cubed is 8. 2 times 2 times 2. Right? You don't need to know what the surface areas are. You don't need to know what the volumes actually are. This is the relation, and it's not saying that the volume is 1 and the volume is 8. It's saying that their relationship would boil down or simplify down to 1/8. Okay, so this isn't going to give you what the actual volume or areas are. It's just going to show the relationship. Okay? What about these? Are these cylinders similar? Do those corresponding parts have the same relationship? Are those the same?
Yeah.
Okay, so they are similar. So what would the scale factor be? 1/3. Their areas. Okay. Volumes. 1 to 27. Remember, it's the first dimension that you're cubing to get to the volume, so don't accidentally cube this. Always make sure your foundation where you're starting is that platform of the first dimension. Okay, so that's one way you can use the staircase to answer these questions, just to find those relationships based off of the scale factor. Questions on that? Okay. The next set of questions is a little bit different. They're already telling you that they're similar, so we don't have that part of the question to worry about anymore. They are telling you that these are similar solids. They're after the scale factor. of the smaller prism to the larger one, so that they want the numbers to be increasing order when you guys are writing the scale factor. Now this is where the staircase is going to be especially helpful. What dimension is scale factor in? So they want our answer to be in terms of the first dimension, but we're not in the first dimension for any of these. We need to take consideration of what dimension am I in, what information are they giving me in the question, and where do I need to be, and then take the journey to get there. So what dimension am I in here? I'm in the third dimension because we're talking about volumes right now. I need to go all the way down to the first dimension. How would I do that? Cube root. So I'm going to take the cube root of the ratio of the volumes to go down to the first dimension. And you can do this in your calculator. There's a button, you math option 4. It will give you a decimal, but you need to turn that into a fraction. Scale factors should always be fractions. 9/11. And again, this is not saying that the sides are necessarily 9 centimeters and 11 centimeters. You're saying that the relationship of those side lengths would boil down to 9/11. Alright, so everybody see how I did that? I went from the dimension I was in to the dimension the question was asking for. This one is also in the third dimension, so I'm going to also take the cube root. The only thing that's different for this one is that there is a pi. Now it will be easier for you, because there's a pi on the top and the bottom, to just ignore them. You can kind of cancel them out from the top and the bottom. So all you're really typing in is 250 divided by 432. And you're taking that cube root. I can't remember if having the pi there or not actually messes up the calculator. So my advice would be just leave out the pi, so you can cancel them anyway. So you're going to take the cube root of that, and you don't have to put the pi's back either. Pi's cancel out, they're gone. What would your scale factor be when you take the cube root of the ratio of volumes? 5/6. What's different about the third one? This is surface area, so what dimension would I be in? Area is in the second dimension. So this time I would take the square root. This I'm going to take just the square root, and again, you can cancel out the pi's. Just use the 20 and the 125. 2/5, yep. So anytime when you're working with similar solids, when it's two shapes you're comparing, they're similar, they're asking you to find a scale factor or a ratio, you need to figure out, do I have the information in the correct dimension? And if not, you need to figure out how to go down or up the staircase, to get to the dimension that they want you to be in from where you are in the question. Okay? So sometimes these questions can be hard to recognize that this is what you're supposed to be using the staircase for this question. So anytime you guys are looking for a ratio, scale factor, or any of these ratios, that's a staircase question. You just need to figure out, am I in the dimension already, or do I need to make a change? And then you would use those rules. Alright, questions about those? Alright, our last two questions on this page are a little bit different. They're asking us to actually find values. So the previous questions were just asking for ratios, comparisons. These two questions are actually asking for values. What is the volume? What is the surface area? This is still working with similarity though. Okay? So first of all, if they're asking for the surface area of a cylinder, let's go ahead and write down that formula. 2 pi r squared plus 2 pi rh. What do I need to know in order to find the surface area? And the rate. I need to know those two things. We're focusing on the larger cylinder. Do I have those two things for the larger cylinder? What am I missing? How do I find it? Proportion. That's why we have similar solids here. We can use proportion. 3 to 5 is the same thing as 7 to h. Variable that I need over here. So you can real quick use a proportion to find that missing piece that you need in order to solve. So it becomes 11.7 approximately as your height. And then you can plug that in. So 2 pi radius squared would be 25 plus 2 pi 5 times that height we found already. numerically it becomes 50 pi for the first term, and then 2 times 5 times 11.7 comes out to be 117 pi, and then when you combine them, you get a total of 167 pi meters squared. Right, so this is just another context in which you guys can use similarity to help you solve with these solids. It's different than the ones we were just seeing. You didn't have to go up or down steps or anything like that. This is just another way you can use proportions, similarity, stuff like that to help you solve. Alright, go ahead and do the one on the right. We have 2 pyramids. I want to find the volume of the bigger pyramid. You have the one side of the square base here, one side of the square base here, and you know the height of the smaller one. So go ahead and find the volume of the bigger pyramid using the fact that they are similar. What did you guys get? 768 units cubed. Should get, after you do the proportion, the height of the larger pyramid would be 16. And you would use that to find the volume because it's a square base. You should, I know the markings are a little fuzzy, but all the sides are the same. So the area of the base for this one would be 144 times 1/3 times the height, and you would get 768. Alright. Now, on the next page, we're going to be talking about things a little bit different. We're still using that idea of comparing things and talking about similarity, but we're going to work with it a little bit differently. So this first one here, it says the ratio of the volumes of 2 spheres is 64 to 125. I want to know what the ratio of their surface areas would be. So this is, again, a ratio question. When you guys see find ratios, this is using that step process. Okay? The ratio of the volumes of 2 spheres is this. What dimension am I currently in? Which dimension do I have information for? What dimension do they want me to go to? The second. There's no direct path. So how do I take this information? I know what the ratio of their volumes is. How do I take that and get the ratio of their surface areas? You have to go down to the first dimension and then up. So let's go to the first dimension. So 3D to 1D. You're going to take the cube root of that. The cube root of 64 is 4, and the cube root of 125 is 5. Sorry? Right? So we're in the first dimension. We need to go up to the second dimension now, so we would then square those. That would be your final answer. So this is an example of trying to go between those 2 steps that don't have a direct pathway. You would have to figure out how to bypass that, go down, go up, vice versa, depending on where you started and where you're trying to go. So that's just an example of that kind of situation as well. So again, anytime you guys see ratio, find a scale factor, and they give you one dimension and you're trying to shift to a different one, that's the staircase method. Is everybody okay with being able to recognize that type of question? Okay, then we're going to switch to something entirely different. So these next questions that we're going to look at is trying to see how the volumes or surface areas or something about a shape will change if you adjust a dimension. So let's say you had a cylinder with set dimensions and all of a sudden you make the radius 2 times as big. What does that do to the volume? Does the volume also become 2 times as big, 4 times as big, 8 times as big? That's what we're going to be talking about here. So these next questions are, this little section is just figuring out what the change is. This next little section is once you find what the change is, then actually find the value. So we're just going to start with this one. This is our foundation. It's really simple how you would do this. You'll see, you'll be like, oh, do that in like 10 seconds. So what you're going to do is you're going to write the formula in question. So what are we trying to see is changing? You're going to apply the change. So is the radius 2 times as big? Is the height 3 times as big? Whatever. You're going to apply that to the formula and then see how that results or what the change is compared to the original. So just like this. It says how much would the volume of a sphere change if the radius is doubled? So I'm going to write the volume 4/3 pi r cubed. That's the volume of a sphere. I'm going to write out the formula. Then it says that the radius is doubled, so I'm going to write it again. How would I write this if the radius was doubled? 2r, like this. And then you just need to do some algebra to work it out. So do you guys remember what happens when you have a set of parentheses with stuff on the inside with a power on the outside? If there's no addition or subtraction, you distribute. So it becomes 4/3 pi, what's 2 cubed? 8 r cubed. All right, you're done basically. Now you're going to compare the result here to the original. What's different? It's 8 times bigger. If the factor that you guys see is bigger than 1, that means that it was growing. If it was a fraction like 1/3 or 1/4 or something, it would have gotten smaller. Okay, so that's really all there is to it. Okay, so again, over here, how much would the surface area of a sphere change if the radius is doubled? Now we're looking at the surface area. So that's 4 pi r squared. Same thing is happening. The radius is being doubled. So that would be 4 pi 2r squared. When I work that out algebraically, what does it turn into?
4 pi 4r squared.
So what's the change between the result and the previous? The original and the new? 4 times bigger. Okay, see how we work with that? Okay, this one, how much would the volume of a cylinder, pi r squared h? Is that it?
Yeah.
Okay, pi r squared h. How much would the volume of a cylinder change if the height is tripled? So it's going to be pi r squared 3h. Now for this one, is there a power I have to distribute or anything?
No.
Is there any extra algebra I have to do? So then what's the change? Just 3 times bigger. If there's no power associated with the variable that's changing, then it's just going to be the same change as what you made to that variable. Alright, next, how much would the volume of a cylinder change? Same formula, but this time the radius is halved. What does that mean? How would I write it? 1/2 r. So then what does my formula turn into? Pi 1/4 r squared h. Because when you distribute a power to a fraction, the top and the bottom both get squared. So it's the 1 squared over the 2 squared, 1/4. So then what changed? The volume would be, it would be 1/4 as big or 4 times smaller. Well, I'm just going to say a fourth as big, I think is probably the language they would use. 1/4 as big. Probably the best way of saying it. Alright, this next one is a little bit different. What's different about this one? There are 2 changes, changing 2 different things. Okay, so this one, it's the same idea, you just have to be really careful about your last step. So this one says the volume of a cone, 1/3 pi r squared. Okay, this is my formula for the volume of a cone. I'm changing 2 things. I'm going to double the radius and triple the height. So my new formula would be 1/3 pi 2r squared 3h. So let's do some algebra to neaten it up. The 1/3 pi wasn't really changed at all. What does this little section turn into?
4 pi r squared.
4 pi r squared, and then this stays 3h. Now, there are 2 new numbers that showed up, and all the other ones, there's just 1 new number that showed up. There are 2 here. So how do you think you kind of weigh both of those to get your final answer? You're going to do what? You would actually multiply them. You're not going to add them, you're going to multiply them. So what would the, what are we looking at? Volume. What would the new volume be? 12 times as big or 12 times bigger, whatever language you want to use. So whenever there are two changes, and you notice there are two new numbers that pop up in your formula, you would take those two and you would multiply them together to get the full change. Okay? Questions about that? Alright, moving right along. So this next little section is going to be exactly the same thing with one extra step. Not only are we going to find out what the change is, so we're still going to find, is it 2 times as big, 4 times as big, 5 times as big, whatever. Once you find out what the change is, they're going to ask you to actually find the literal value. So you're going to do the exact same thing that we were just doing to figure out what the difference is, and then multiply that times this. So let's say we were doing this and we found out the volume, wait, what are we looking for? Area. Let's say we find that the area was 2 times as big, then you would just multiply this times 2. Just one extra step to get an actual value of that area, volume, whatever they're looking for. So for this one, we have a scale factor of 2 circles is 3 to 2. The area of the larger circle is 81 pi inches squared, and I want to find the area of the smaller circle. So I'm comparing two things. What I want to do is figure out what's the change. What's the change going from one circle to the other? Once I figure that out, I can then multiply that times the previous, or the original area to find the new one. So let's write that formula, just like we did before. What's the area of a circle? Okay. Now we have to figure out what's the difference between the two. Now this one's a little bit weird because they buried that information in a scale factor. In all the previous examples, they said the radius was doubled, or the height was tripled, or stuff like that. They used very specific language. This one's not using that. It's burying the information in a scale factor. How could I translate that into the same kind of thing we were doing above? If I know the scale factor is 3 to 2. What's the only dimension, by the way, here? The radius. So that's obviously what we're talking about. The radius of the two circles, they're in a scale factor of 3 to 2. So what could I say, about the radius of the smaller one?
Pi 2 R's 2 pi.
Louder? It's 2/3 as big. Okay. If the scale factor is 3 to 2, the 2 represents the smaller of the two circles, so the radius would be 2/3 that of the larger one. So when I rewrite the formula, it would look like this. Because we're talking about the small, I know they wrote it in reverse. They wrote the big to small here, but we're focusing on the smaller circle, so you need to switch that. You can switch the scale factor whatever order you want, just as long as it's matching the question here. So I switch it to 2/3 to really get the smaller circle in the front, because that's my focus here. And I can write that as a fraction, 2/3. So the radius of the smaller one's 2/3 as big. So then what would my formula turn into? 549. Okay, so how big is the second area compared to the first? It's 4/9 as big. So if the original area was 81 pi, and I want to find the new one, it's 4/9 as big, so I'm going to multiply 81 pi times 4/9. Would you keep your... Yes. So you would just multiply the 4/9 times the 81, and you get 36. That's it. So it's the same kind of thing. I know the wording is much different, but whenever they're asking you to find a volume of a similar shape or something like that, and they don't give, notice, if I just told you what the radius was, if I just said, hey, the radius is 4, find the area, you'd be like, formula, done, right? I didn't give you the information to do that. So these questions are when I don't give you the actual dimensions, I'm just telling you their relationship. When I'm giving you a relationship and want you to find another volume or area, this is the process you would use. Okay, so just take stock of what you know, what you don't know, and that'll guide you. All right, this next one, a cube with a volume of 216 inches cubed has its dimensions cut in half. What will the new volume be? So let's write the formula. Always start with the formula, that's your foundation. So this is a cube, which is technically a rectangular prism, but all the sides are the same. So for a rectangular prism, the volume would be length times width times height, but they're all the same. So I'm just going to call it S for side cubed. Length times width times height, all the same. Just call them S times S times S, S cubed. Everybody see how I got that? Quick explanation. Pretty good. Alright, what's happening? This is where it starts. This was his nice little quid pro quo, whatever, normal thing. What's happening? They're all being cut in half. So the volume formula would really be what? Would really be this. Each side is being cut in half, so it's 1/2 s cubed. And so what does that come out to be when you actually do the algebra?
1/8.
1/8 s cubed. So you can see the formulas are very similar. What's the only difference? It's 1/8 this big. So if the original was 216, the new one is going to be 1/8 of that. It's shrinking, it's getting smaller. That turns out to be 27 inches cubed. Alright. Next one, we have the surface area of a blue ball is 64 pi meters squared. A different ball, a red one, has a radius that's 3 times as big. And I want to know what that one's surface area would be. Again, if I had just told you that the red ball had a radius of 6, plug it into the formula and be done. But I didn't tell you what the radius was, did I? No. I just gave you a relationship between the two. So that's ratios. That's when you have to use this kind of process. So the surface area of a ball or sphere is 4 pi r squared. What's happening? I'm shifting into one where the radius is, so 4 pi 3r squared, which is 4 pi. Okay, so how do they compare? The volume would now be 9 times bigger. So I'm going to take the 64, that's weird, 64 pi, multiply it times 9. Obviously it should be getting bigger because the radius is growing. What do you get? Pi. Okay. Couple more. Waffle cone. A large waffle cone can contain a volume of 102 pi inches cubed. A small waffle cone has a height that's 1/3 the height of the larger cone. What would the volume of the smaller cone be? Again, if I just gave you what the height was, you could find it real easily, but I didn't do. Volume of a cone. Okay, then what's happening? What am I changing? The height. So you still have the first part same, but the height, does the height have a power associated with it? No. So when you're changing a dimension that doesn't have a power associated with it in the formula, then the change stays the same. So if you're making the height 1/3, then the change would be 1/3 for the volume. So if the original volume was 102 pi, you want 1/3 of that. Which is 34 pi inches cubed. Alright, now the very last one is a teeny tiny bit different, and I want to see if you guys can figure it out on your own. Teeny tiny bit different. It's not that closely related to the ones we were just doing, but I want to see if you guys can figure it out anyway. So go ahead and read this last one. See if you can figure out how to use the information they provided, and see if you can figure out what the answer would be. So I'll give you a couple minutes to do that. Compared to the others. Okay, so first of all, it goes from surface areas to volumes. What else is different? That prevents you from doing what we were doing above.
There's no change.
There's a change to just represent it as a ratio, just like we did before, but what's different about this question that prevents you from doing what we were doing above?
area times volume.
We've already noticed that it's from surface area to volume. We don't have a formula. Did I tell you what shape it was? No, we don't even have a formula. Okay? So we can't do that same kind of thing we were doing before, but it is important to notice that I'm going from the surface area relationship to the volume relationship. So this is kind of backtracking to what we were talking about before. If you guys see this kind of scenario, which is similar, it is connected to this, but I don't know what kind of shape it is. So I can't use the formulas. Instead, I'm going to have to use that kind of proportionality relationship between these two, because I also noticed the word similar in this question. So first of all, I'm in the surface area relationship here with the 4 to 25. That's in the second dimension when I'm trying to get to the volumes, which is in the third dimension. Can I go straight there? So where do I need to go? I need to go down to the first dimension. So if I know the surface area relationship is 4 to 25, what's my scale factor, or the relationship in the first dimension? 2 to 5. So I know that the relationships between their scale factor, their individual dimensions, is 2 to 5. But that's still not where I want to be. What dimension do I want to be in? What dimension am I really dealing with? The third dimension, because I'm trying to find the volumes. So I'm going to take that, go to the third dimension. How do you go up to the third? You're going to cube. So you go down from the second step, and then you cube that to get up to the third dimension. So this is my relationship between the volumes. Now how do I use that to find the new volume? A proportion. So I have 8 to 125. These are not the actual volumes. Those are representative of the relationship. So I'm trying to find the smaller one, the actual volume, represented with X. Then the actual volume of the larger one is 120. This is a relationship. These are the actual numbers. So then I would set up a proportion and cross multiply this all. .68 meters